A warm welcome, student. In this video, we will discuss about a principle of HSAB principle. Its application and its limitation. In 1963, Pearson gave a simple rule for predicting a stability of the compound from acid and base, which is come to known as HSAB principle. According to this principle, hard acid prefer to combine with hard base and soft acid prefer to combine with soft base to give a stable complex. Hard acid and hard base give stable ionic complex. Soft acid and soft base give a stable covalent complex. But hard acid and soft acid doesn't give stable complex. Soft base and hard base doesn't give a stable complex. This principle is also known as HSAB principle. So, the larger the electronegativity difference, between the hard acid and hard base give rise to strong ionic interaction. The larger the electronegativity differences between the hard acid and hard base give rise to strong ionic interaction, because the electronegativity of soft acid and soft base, similarly the electronegativity of soft acid and soft bases are almost same and hence have less ionic interaction. The interaction between them are more incovalent. The interaction between hard acid and soft base or soft acid and hard base are almost polar compound to give a polar covalent and tend to be more reactive or less stable. The more the reactive, the less the stable of the complex. The more the reactive, lesser is the stable. So the polar covalent compound readily form either more ionic or more covalent compound if they are allowed to react to a given complex. Pearson classify a hard acid and hard base, hard acid into hard and soft, base into hard and soft. So these hard acid are very small ionic radii. They have high positive charge, not easily polarized. The common example is lithium plus, beryllium 2 plus, aluminum 3 plus, chromium 3 plus, iron 3 plus. They are hard acid. Soft acid are the cation of larger ionic size, radii size. They have low positive charge. They are easily polarized. Example is Ag plus, Pt2 plus, lead and platinum 2 plus, mercury 2 plus, etc. Whereas the hard base, since you know the hard base has something to do with nucleophile, so it has a small radius, it has high electronegativity. The electronegativity like fluorine, chlorine, all these are electronegative compound. So donor atoms with low polarizability. Some examples like water is one common example. It is 2 lone pair. Ammonia, it is 1 lone pair. And fluorine, the halide, and ROH. This is the example of base, hard base. Soft base are very large ionic radii. They have low electronegativity. Donor atoms with high polarizability. Some example is iodine, cyanide, R2S, R3 phosphorus, etc. So these are some classification, and some powder acid are there. But these four is very important. Okay, now let's come for the application of HSAB principle. Before we move to application of HSAB principle, you have to know a classification of hard acid and soft acid, hard base and soft base. So I've made a dedicated video for the classification of hard and soft acid. You can go and check in the playlist. It is there in the acid and base and the classification. Okay, so one of the application of HSAB principle is to determine the stability of the complex. So hard acid and hard base always give a ionic stable complex, and soft acid and soft base also give a covalent stable complex. So suppose you have an example like Ag plus, it is a soft acid. When you react with the soft base, you get a stable soft complex will be formed, Agi2 minus. This is soft complex. And they are stable. Another type of example, like you can have a Ag plus, this is again soft acid, and 2 molecules of, this is a hard base. As you know that this fluorine is a hard base, so they give a AgF2 minus. So these are soft hard complex, and they are unstable, because the HSAB principle says hard acid and soft acid give a stable complex, soft acid and soft base give a stable complex, but hard acid and soft doesn't give stable complex, hard base and soft base doesn't give a stable complex. So this is stable and this is unstable complex. This is the one type application of the HSAB principle. Another application of HSAB principle is HSAB principle, hard and soft acid and base principle. It predicts the feasibility direction of inorganic reaction. HSAB principle is used to predict the outcome of few of the reaction. We can predict whether the reaction proceeds to the left, or whether the reaction proceeds to the right or left based on the soft or hard acid and base interaction. So some examples, like suppose you have a lithium iodide and CSF, calcium chloride, always proceed to give a LiF and calcium iodide. There is more stability product due to hard and soft combination. So that is the reaction goes like this. Li lithium iodide, this is a hard acid and soft base complex, plus CSF, calcium is a soft base and yes, this is soft acid and hard base, this is soft acid and hard base. So when these two react, it give this lithium has a capacity to accept an electron electron pair. So this fluorine will go and attack this, and lithium LiF you will get. So this is hard. Both are hard. This is hard acid and hard base. They will combine. Hard you will get, plus remaining is H2, or you can, yes, this is CSI you will get. So this is soft acid. This is a soft acid, and so soft acid, and iodine is also a soft base. So this is how you get. And another type of example is, you have, suppose you have calcium sulfate react with the hard base. So hard soft, this is a hard acid and soft base. Hard acid and soft base and hard base. When it react, you get this will go, negative charge will go and attack this, and you get CaO, calcium oxide will be formed. This is hard acid and hard base, and you get H2S you will get. So these are some examples. Another type of example is, suppose you have copper iodide 2, and this copper is a hard acid, and this is a soft base. So it react with copper iodide, react with 2 molecules of, this is copper is a hard acid, and fluoride is a hard base. So when it react, you get the Cu will go and attack this iodide, and F will go and attack with this chlorine. So this CuF2 you will get, that is hard interaction will be from hard acid hard base product you will get, plus 2 molecules of, you will get the 2 molecules of Cu iodide will be formed. This is soft. So soft acid and soft base. This is how you get the product in the right direction. Another type of example is the reaction between the AsF3 and Bi3 is possible and proceed to the right, since this arsenic As3 plus is softer than B3 plus, and iodine I minus is softer than fluorine, because this is a soft base and this is a hard. So this both arsenic 3 plus ion and phosphorus are softer. Phosphorus 3 plus are softer because, but relatively this arsenic 3 plus is softer due to larger in size. Because of that, it pulled the right direction. So this is the reaction when AsF3 plus Bi3 react, you get the AsIL3 plus BF3 you will get. And another type of reaction is the reaction between the magnesium sulfate and barium oxide. So this magnesium, if you see this reaction, you will get the Mg2 plus is hard acid. It is a hard acid as compared to barium. This is also both are hard acid, but this is much harder than this Ba2 plus and O minus. So this magnesium will oxygen will go and attack this barium, and barium sulfate will be formed. So B2F4 can be prepared by treating this phosphorus. This is not the right structure, but the structure will be something like this. So this B2F4, this can be prepared by treating with BF2I with mercury. HC is mercury and this is a reaction. So since you know that this iodine in this complex, this iodine can be removed, because fluorine, as you know that fluorine is electronegativity, and the iodine is a much lesser electronegativity. But since this iodine is a soft base, it can remove faster as compared to this fluorine. So in this reaction, iodine can remove instead of this fluorine, and this, when the reaction is 2Hg, it will form the 2Hg ion is soft acid. This is a soft acid, so it always prefer to combine with the soft base. So here the soft acid and the soft base is iodine is a soft base, so it will go and attack this soft base, and you get the two molecules of HCl2 and B2F2 product will be formed. So don't forget, soft acid always prefer to attack with soft base. So in this reaction, the mercury Hg is a soft acid, as we have discussed in this video also. This mercury is a soft acid and iodine is a soft base, so it will always try to interact. So this can also release negative charge, but as comparing to fluorine and iodine, the iodine will remove faster as compared to fluorine. That's why it can go easily bind with the mercury soft acid. It is a plus size and negative charge. Both are negative, but this will remove faster. So in this way, you will get the product. So these are the two types. It gives the feasibility of the reaction. Another types of applications of HSAB principle is hard and soft interaction. Hard and soft interaction over hard soft interaction, that occurrence and formation of important ores and minerals in the earth crust. So this principle also gives different types of hard and soft classifications. So hard acid, soft acid, hard base, soft base. So we have discussed enough classification. Hard acid are smaller in size. Example like sodium, potassium, magnesium 2+. All these are some example of the, or manganese also you get, and aluminum 3+, Fe 3+. They are all hard acid. Soft acid like you have Cu plus, silver plus, silver ion, calcium ion, mercury 2. This is a soft acid, mercury 2+, cadmium 2+, Pt 2+, etc. So hard base is, you have halide like chlorine, fluorine, oxide like you have O2-, and soft base is iodine, we have discussed now also, S2. So this HSAB principle also gives the different types of ores and minerals on the earth crust, and it gives a different classification of the hard acid and soft base, hard and soft acid. And one type of acid is called borderline acid. So this borderline acid are nothing but sometimes it behave acid and sometimes it behave base. So example like Fe2 plus, it also acts as a borderline acid. Nickel 2 plus, it also acts as a borderline acid. Zinc 2 plus, Pp2 plus, etc. So these are some of the application of the HSAB principle. Okay, so what are the limitations? This principle do not provide a quantitative scale of measurement. HSAB principle does not take into account of acidic and basic character of the compound that form. See, in this HSAB principle says hard acid always prefer to combine with hard base and give a ionic complex, and soft acid prefer to combine with soft base and give covalent complex. So he says like this, but this theory do not give any account on the acidic character of this complex that form in the reaction and the basic character of the compound form in the reaction. So because of that, this was the one limitation. He should have studied the basicity and acidity character. Another limitation is this theory states that hard soft interaction to form product formation is stable. That is, hard acid and hard base and soft acid and soft base give stable complex. The theory says it is a stable complex, but hard acid and soft base react, it give unstable complex. That was the theory, and it is not possible. Hard acid and soft acid is not possible. Hard base and soft base is not possible. But in many compounds were known in which the hard soft interaction are also stable. So it has been formed that he says it is not possible, but when the hard base and hard acid, or when the hard acid and soft base, like some example like hydrogen fluoride is a very hard acid. When it react with the SO3 2 minus, that is a soft base, it give a, so according to this principle, hard acid and soft base doesn't give a stable complex, but actually in this compound reaction to give a HSO3 minus plus F minus. So this is a hard and soft complex, and this is a very hard base. So the compound we form when the hard acid and soft base reaction, it gives a stable complex. Some example like another. So according to HSC principle, the product is unstable. So if we follow this principle, it was unstable, but it is proved wrong, because this HSO3, it is a very strong complex. And another example like you have a, if you have CH3 HgSO3 minus plus hard base, when it reacts, this is a soft complex. When it react CH3 Hg plus O minus SO3 2 minus, this is a soft and hard complex will be formed. So this is a very stable complex compound. So in some reaction, when the hard and soft reaction takes place, the stable complex is formed. So this hard and soft acid base principle, it has a limitation that it proved wrong. So these are the three main objection or limitation of this principle. So in examination, you will see some multiple choice question like this. Suppose you have which of the following is a soft acid? Lithium, sodium, potassium. We have discussed Ag plus is a soft acid. That is very simple. This is it has to be here. Yes, okay. So which of the following is not a hard acid? Hard acid. It is a small ionic. So beryllium, magnesium, they are very small in size. Otherwise, this Ct is large. So it is not a hard acid. So hydrogen fluoride is formed by the combination of, it is a very strong, hydrogen is a hard acid, fluoride is a hard base. So this 3 is the answer. Which of the following is a hard acid? Hard acid. It is small ionic charge. Lithium is a small ionic charge. In this way, you can practice the MCQ. So these are the 3 principles of HSAB theory. If you have any doubt, you can ask me on the comment section or in our chat box, and we can discuss in the upcoming video. Thank you everyone for watching the video.